Hello, welcome back. In this video we're going to be proving a portion of Theorem 4.4, which tells us a little bit about properties of the zero vector. So particularly, it tells us that if we try and scale the zero vector, then we get the zero vector back. From what we understand of vectors, this should make sense. However, remember, vectors can be weird things that aren't just lists of numbers. We might have some weird addition to find, we might have some weird scaling going on, and we need to be able to make sure that the zero vector is always the zero vector. Alright, so let's go ahead and prove this. Alright, so to get our proof started, let's go ahead and let V be a vector space. And C a scalar. Alright, and then we have this if statement here, so we're assuming 0 is the additive identity, so denote the additive identity of V by 0 with a line over it. Now keep in mind, again, V might not be r to the n. It could be polynomials, it could be continuous functions, it could be that weird vector space from the slides last time, right? Whatever it is, we're still going to denote the additive identity by 0 bar. And what does this mean? So this means that for all vectors within our vector space, if we add 0 to it, we should get our vector back. That's what it means to be the additive identity. All right, if we want to remind ourselves of the definition. All right, so in particular, if we add the zero vector to itself, we get the zero vector back. All right. All right. So how can we use this? Well, then let's just create a centered line. C times the zero vector should equal C times the zero vector plus the zero vector, right? We're just doing a substitution there with the additive identity. And then we can use our distributivity. Okay, so distributivity, or by distributivity of scalars. All right, comma at the end of that. All right, so what can we do with this? Let's add minus C times the zero vector to both sides of the equation. C times the zero vector equals C0 plus C0. To get, all right, C0 plus minus C0 equals C0 plus C0 plus minus C0. All right. So again, we're being a little bit careful. All right, minus C0 might not be just make all the values negative, because again, it might not just be lists of numbers. But it does mean that this is the additive inverse. So what does it mean to be the additive inverse? Well, on the left side here, this simplifies to just the zero vector because we have the additive inverse, which is one of the required vector space axioms that these things exist. Right. Here we don't yet have the additive inverse right next to C0. So we should rearrange this first using our associative property of vector space addition. All right. So we'll put associativity here. All right. And then now we have that this is C0 plus 0. Okay. So this would be our additive inverse. And then lastly, this we've just added the zero vector to something, so again we get to use the property of the zero vector being the additive identity. Alright, so let's put the blue period there. Alright, so therefore C times the zero vector is just the zero vector as desired. And we're done with our proof. Okay. So one very important point about this proof that you should be noticing is that we never used lists of numbers. We never pretended we were in Rn or anything. We just used the axioms of the vector space from section 4.2 to prove that if you try and scale the zero vector, you get the zero vector back. Okay. So importantly, that means that this works no matter what vector space we're talking about, which is actually very essential, right? We might have weird addition, we might have weird multiplication, but we know always in our heart that multiplying 0 by a scalar is going to remain 0. And that is very important and very cool. Alright, excellent. So that is that. Have a good one. Bye-bye.